Here we go. Right, guys, it's been a few months since we've all got together. So absolute pleasure to see everyone. I know a lot has happened since we last caught up. So Mike's going to have a lot to talk about, I guess. Anyone that's not met me, my name's Dylan. I'm co-founder of Digitalent. Outside of helping companies scale their product and engineering teams, our biggest focus has been building communities. And AI has been a huge part of that. Everyone is learning on a daily basis. We wanted to create an environment where everyone could share ideas, successes, challenges. And I think over the last year or so, Mike and I have brought some really great people together and had some really great outcomes from this. Mike's a community member of ours, super knowledgeable guy, absolute expert in the AI space, great presenter, and is always there to help and share ideas. So always a pleasure to have him. Mike, do you want to quickly introduce yourself and let's get this started?
Absolutely. Too kind. Your introductions always make me blush. Thank you, Dylan. Everyone, the wonderful Dylan and Digitalent. Thank you very much for once again convening such a wonderful session and community. For anyone who doesn't know me, my name is Mike. It's very nice to see you all in here. I'm a product leader and CPO, technical product manager. I've been an NI and ML enthusiast since approximately 2008. I started playing with neural networks and the old NLTK based on Java, even before I think even TensorFlow was a thing. And since then, I've sort of maintained a passion through my work. Specifically, I get to apply this discipline-specific orientation in my day-to-day job, which makes me feel very lucky. And throughout my work, I manage products and engineering teams that are focused on delivering AI and ML-driven value propositions. And of course, that requires me to very closely follow the AI and machine learning developments in space, and that makes it easy for me to present on the latest developments in AI, which is what we're going to do today. Now, as always, before we get started, I like to include a little disclaimer, right? Because we have a lot of people coming from different discipline areas in terms of what you ought to expect from this talk, specifically in terms of technical granularity that we will be applying today. So I tend to position these particular sessions by highlighting at the beginning that these sessions or these discussions, they don't exist at a 10,000 feet level, but maybe at a healthy 1,000 feet conversation, right? So one way of looking at this is that we will try to make this very accessible or simplify and obfuscate complexity where it really doesn't affect or impact your understanding of the research that we're going to discuss today, but it will also not hesitate to sort of like go deep where it's necessary to sort of like establish a really good grasp of what is going on, right? Now, what that means for you, if you are an AI researcher yourself, right, you're working in the AI and ML space, there is a chance that you might have heard about the things I'm going to speak about today. You may not have heard about them in that particular sequence, which could still be valuable because I framed them sort of in the context of particular themes and trends we've seen throughout the year. But you're probably aware about the general developments in this space because obviously that's your job, right? If you're not an AI or an ML researcher, do not fret. What I hope to do is take you through what I believe are the three most relevant paradigm shifts that we have seen in the AI research space over the last 30 days alone. So all of the papers that we're going to discuss today are really fresh. And then what we're going to do is we're going to sort of like weave a story around this and lets us, particularly product people, I'm predominantly a product person, that allows us to get a feel for where the AI space and the technology is heading overall, right? You can probably also tell that what I'm not going to do is I'm not going to go through every single piece of news and research that has occurred in the last 30 days. We'd be here for months and months and months if that was the case. But throughout this presentation, what I hope to do is that we're going to dive into a few papers that will help all of us put this exciting space and this innovation into context and understanding sort of like the strategic drivers and direction behind some of the discoveries, right? Now, as always, before we get started, we usually start with a little bit of levity. And this time we're going to start with something a little bit heartwarming. Now, I am at this point going to share my screen, which I haven't done yet. Wonderful. And I want to see whether anyone has watched this video. If you're notoriously online like myself, you may have seen this video pop up on your feed. I just wanted to quickly check in with everyone to see whether you have seen this video before. Let me just quickly share my screen here. Google is not being very collaborative, which is a little bit of a shame. Okay, doesn't allow me to share a particular tab. How funny.
We did see that at one point, it did come up.
It did come up. Right, you can see it here. What I don't think you might be able to do is I don't think you will be able to hear the audio. 1 second. Maybe in camera. Okay, 1 second. I'll be right. Oh, sorry. So I'm back. And the reason why I did this is because I was on Edge before, and now you're in the Google browser, which allows me to share this video, and it allows me to share this video with audio included. So I'm going to play this here real quick as a little heartwarming starter, and then we can keep going.
Me and my husband. You okay?
Yeah, hi,
Hi. So husband?
works for me.
Me and my husband.
Excellent. So this is very, very short. And of course, it's a wonderful, cute little love story that people have really enjoyed. The only thing is, of course, it doesn't really exist. So this was partially the very first video that got myself. I did not realize it was AI at all. Essentially, this is, of course, a consequence of the release of the new Sora model, which is OpenAI's new video general release about 2 weeks ago. But what makes this video significant is that it has been touted as sort of like the officially accepted confirmation that AI video is now indistinguishable from real life video. And we all knew that this moment was about to come. And frankly, I'm relieved that it was this kind of video that made us realize this. But it also shows the power of these models and the fact that we are not probably not really hitting a threshold where we're seeing that progress taper off, right? Now, in terms of setting the scene for today, right? As we touched on in the last session, so the last one before this, it was about 2.5 months ago, much of the progress that we've seen across large language models has supposedly been enabled by the shift towards reinforcement learning. And mind you, this does not apply to the Sora 2 video model because it's a latent diffusion-based model that doesn't use any much of reinforcement learning to begin with. But this segue was always going to be really hard, so I just stuck with it. We needed something to start off this presentation in a lighthearted manner, so that was what I decided to go with, right? Now, the fact of the matter is that many prominent model providers have highlighted their intention to increase the portion of reinforcement learning, which obviously has tremendous upsides for them. But over the last month or so, we've seen papers come out that offer a counterbalance to the reinforcement hype. And one of those papers came actually from OpenAI itself. And it's about hallucinations, right? And this is a really good segue, see what I did there? Because hallucinations sort of like stood at the center of one of the most popular and dare I say viral papers that we have seen here throughout the September timeframe. And frankly, I would be kind of amiss in offering a recap of the most paradigm shifting papers if I essentially left it out, right? Because ultimately, for what feels like ages, we have heard that and experienced that hallucinations have been described as these mysterious, almost magical emergent behaviors. And the fact of the matter is that hallucinations have somewhat been accepted like some kind of ghost in the machine that we just have to live with, right? But this paper from OpenAI was a paper that challenged this notion directly because it strips away some of the mystery that is associated with that behavior and doesn't tout it as emergent, but touts it as a direct consequence of a particular training techniques, right? So when we, I want to be clear, right? When we say hallucinating, we don't just mean simple mistakes like getting a simple number wrong or a date wrong or slightly wrong. We're talking about models spitting out information that is fully incorrect, often completely made up, but is also delivered with this audacious and unwavering confidence, right? It's the model's refusal to simply say, I don't know. It's a refusal to admit any uncertainty, right? Now, OpenAI has included some examples in their paper, of course, right? So this first question is, what is Adam Tauman Carlyle's birthday? Now, it's worthwhile highlighting that the model was trained with the answer to that question, and the correct date is known to the model. But when OpenAI tested that with various models, some of their own, some open source LLMs, they essentially asked, I think, DeepSeek, GPT-4, and Llama. It gave 3 totally different and completely wrong dates, right? It came back with, you can see here, 0307, 1506, and finally 0101, like completely random guesses, right? But each of these, and we're all familiar with this in some capacity, was sort of like delivered with absolute confidence, like not a hint of uncertainty. And that refusal to abstain, right, to just guess over and over again, that's the exact problem that this paper addresses and that we're talking about when we're talking about hallucinations, right? And it also tends to get more severe with more complex facts. So the second example here, they asked 3 of the most popular models about Adam's PhD dissertation. The correct answer was, I believe, 2001. Yeah, here we go. Down here it is. But each of the models, again, gave a different wrong title, a wrong year. I think it even put him in the wrong university at some point, right? And so whenever it gave those responses, however, whenever the models gave those responses, they didn't just give the wrong responses, but they provided those responses with absolute certainty, definitive language, zero hedging. Now, the paper is, I believe, one of the most compelling attempts at offering an explanation as to why that is. It argues that these confident falsehoods come from 2 very predictable places, right? First, there's the inevitable statistical noise that gets baked in during pre-training. We're going to talk about that here in a second. And second, maybe more shockingly, there is an evaluation system, that's the one that we humans built around LLMs, that's fundamentally flawed. So if we look at the first one, right, obviously we have to ask ourselves, well, what is the problem with the pre-training process? Why do these base models make these mistakes, even if we assume that the training data was perfect? And to explain this, for anyone who isn't familiar with this space, we need to take a really short detour into the 2 major phases during the LLM training process, and that's the pre-training process and the post-training process, right? So first up, generally, when we train LLMs, we have, and I'm abstracting here a little bit, of course, but in general terms, phase 1, we do a thing called pre-training. This is where the model sort of builds its absolute foundations of language and knowledge. You can imagine this is essentially exposing the LLM to truly massive and diverse data sets. We're talking hundreds and thousands of books, a huge slice of the internet, articles, you have it. Right, and in this phase, the LLM, one of its only jobs is to get really good at predicting the next word in a sentence. That's what you've heard before, right? We've all heard before the saying that LLMs are just, word predictors, which is not entirely true, but this is where that comes from, right? It comes from phase one, it comes from the pre-training, right? And through that one simple task, it then starts to understand things like grammar, facts, and patterns of reasoning. But here's the critical part. This whole phase one is completely unsupervised. There are no humans in the loop telling it what's right or wrong. That's where the second phase, however, is supposed to come in. That's post-training, right? And that's really important because that stage is all about fine-tuning the model's behavior, right? We want it to be more helpful, we want it to be safe, we want it to be aligned with human values, right? And here we're using techniques like supervised fine-tuning and, of course, reinforcement learning, which we talked about before, right? Specifically also often driven by human feedback. So humans look at the responses that the models give and they provide it with feedback, right? And a lot of times, right, when people will actually review and score these model outputs, that process teaches the model what a useful, respectful, and accurate answer actually looks like, right? Now, the hallucinations derive from these distinct two phases, but in different ways, right? So the paper argues that hallucinations actually start out as a simple error in binary classification during pre-training. So in other words, during that pre-training phase, the model sometimes encounters sort of like yes or no binary classification like decisions, such as distinguishing factual from non-factual statements, right? Without any explicit feedback, because that's unsupervised, remember? And for example, if it was to see an incorrect fact, like the Eiffel Towers in Berlin is often an example that's being offered. If it sees that often enough, it might learn to assign that sentence a high likelihood of accuracy, even if it's incorrect. And when you consider that, you know, many LLMs are essentially trained on, amongst other things, a lot of Reddit text, you can probably understand why errors like this might sneak in, right? But that is obviously a tangential statement. So the question is, how did the researchers know that for a fact? And what they did is they sort of identified a really solid link between the model's overall generative error rate and how badly it performs on basic questions around, is this a valid statement? So basic classification tasks, right? In other words, you can think of it as it's always easier from a statistical and computational perspective. It is, maybe I should put it differently. From a statistical or computational perspective, it is harder to generate the correct answer from scratch than it is to simply check if an answer is valid. It's the difference between recall and recognition, right? You can see that for yourself, right? It's easier for you to recognize a face than draw one from memory, right? And while the models are being trained during the pre-training phase, right, they're being trained to predict the next word, it is forming these internal associations, right? And while it creates these associations, it creates this statistical ease. It makes it easier to compute for the LLM to create predictions based on the things that it learned during the pre-training. And that leads to errors creeping in during the much harder generative phase, right? Now, what leads to those errors happening or guarantees for those errors to happen is several factors, but mostly it comes down to two aspects, right? The first aspect is a thing that the paper called the singleton rate. So this relates to what's called epistemic uncertainty. So those are facts that are arbitrary, rare, and they have no clear pattern. So these are things that you need to know rather than figure out, like birthdays, for instance, have a high degree of epistemic uncertainty, right? They're a classic example. Single addresses, right? Because they're just unique and you might, you know, only find references to a particular birthday or a particular address once in a document. You know, if you have hundreds and thousands of documents, that just gets buried with all the other information. And the core finding in this paper is that the hallucination rate after pre-training is at least the fraction of facts in the training data that appeared only one single time. So if a tiny detail about a person is mentioned in just one book once, right, out of billions of documents, that fact is inherently unstable for the model. If 20% of unique biographical facts are singleton facts, like Hemingway liked sardines, for example, right? The model is statistically expected to hallucinate at least 20% of questions about those facts, right? It's statistical noise that you cannot filter out, but it's also not just sparse data, because the second aspect comes in here, which is sometimes the models aren't capable enough, right? This is where we see what the paper called intrinsic hallucinations. And if you've been here before, right, you would have probably heard about the strawberry problem, right? Which used to be an issue when you ask certain LLMs how many R's are in the word strawberry, would give you a wrong response, right? And the researchers called this the poor model problem, right? What's happening here is that the architecture isn't actually reasoning or counting the R's in the word strawberry, or the D's in the word DeepSeek, which is the latest example from just a few weeks ago. What it does is it will instead fall back on the statistical patterns of how often an R occurs before an A, for example, right? And it does so because these statistical patterns have been baked in during pre-training, and it is computationally easier for it to look at these patterns than to split up the word into individual characters and count it, right? Computers are inherently lazy, so are LLMs, right? But that's not the only reason, because where it gets really worrying is this is just half the story. Because if you just paid attention, right? Post-training, you might ask, isn't that designed to address that, right? That's where the humans come in, right? So the question is, why doesn't our post-training and alignment end up fixing this, right? Why do these confident falsehoods stick around and even get polished up? And yes, you can't ask the strawberry question anymore. That had to have been addressed specifically with a bug fix release, it turned out, right? But generally, why do hallucinations still happen? And why do they happen with such confidence? And the answer is surprisingly simple and sadly a little bit depressing. LLMs, by their nature, are fundamentally optimized to be good test takers, right? They sort of behave like the ultimate A student who always has an answer. If you think about taking a, let's say, standardized test at school, right? If you're unsure about the answer, what do? What's the best strategy? You guess, right? And you guess as long as there's no penalty for being wrong. And right now, the vast majority of benchmarks that are being used to evaluate every new model against, so this is GPQA, MMLU, SWE-bench, and many of the other benchmarks, right? They use a really standardized binary 0 or 1 grading scheme, right? You get 1 point for providing a correct answer and 0 points for saying, I don't know. And under that system, guessing always maximizes your expected score, and make sure that the model that you've just spent months and millions of dollars of training will have a higher score during benchmarking, right? And of course, this creates a truly perverse incentive, because an honest model that admits uncertainty will always be outperformed on these benchmark by a model that just guesses. And our system therefore actively penalizes honesty. because performing well in the benchmark is directly associated with investment decisions, right? And therefore, the model trainers, they have currently little incentive to build a model that just says, I don't know, right? And OpenAI, or the researchers at OpenAI openly acknowledged it, right? The paper suggests that to reduce hallucinations, we should be fixing those benchmarks and realign the incentives to reward honest and calibrated uncertainty, right? But they also say that it's nigh impossible because of the current landscape, right? Now, to the next paper. Where this particular hallucinatory behavior especially hurts is our model's ability to truly generalize complex reasoning, but particularly over long periods of time, right? Arguably, this is something that our human brains can really do well, but LLMs do end up failing reasonably quickly over long reasoning contexts and a lot of turns when they have to reason through a particular problem over an extended period of time, right? Human brains don't have that problem, right? So researchers have asked themselves the question of how do we build models that don't just calculate, but can generalize complex reasoning over long periods of time, right? Just the same way the human brain does. Now, this is a massive architectural puzzle and arguably one of the toughest nuts to crack in the AI space at the moment. On the one hand, we have the transformer architecture, which is absolutely brilliant in performing dense tensor math. So tensor math is like multi-matrix multiplication across various layers, those kinds of things, right? And this is very useful. We get powerful models out of it, but it's just different and not as good as the brain when it comes to these extended generalization tasks, right? But the problem with the brain is the brain in and of itself, and maybe I can show you this here a little bit because the image is a little bit small, right? The brain is sort of like a messy, distributed, vastly complex graph-like system with, our neurons predominantly representing the nodes and edges of those really complex graph. And what happened is that trying to map, right, one architecture directly onto the other has always felt like there was sort of like a missing link between those two. Arguably a consequence of that is that, yes, we do get these really powerful models, sure, but predicting their behavior reliably over the long haul, that remains extremely tricky, right? But the good news is that the researchers had somewhat of a breakthrough. And I would argue that this paper probably describes the most significant innovation in AI architecture since attention is all you need. It was that seminal paper that kicked off the entire LLM revolution. Now, why is the brain so powerful? Well, the reason why the brain is so good at generalizing the complexity over long periods of time is because of a key property that it has. And that is the brain's network in itself is scale-free. So a scale-free network is a type of network where you have a few nodes, and those are called hubs. They have many, many more connections than others, right? These networks follow sort of like a power law distribution, meaning that most nodes only have a few connections, but a small number have a really huge number of links. So, for example, if you look at this right here, this is a visualization of a scientific collaboration network, right? You have certain individuals that are acting as influencers. They're connected to absolutely everyone, and others are more focused on their particular area of expertise, and they might be, connecting with a bunch of others, right? The same applies for the internet. If you think about Google being connected to absolutely every website out there, that's their mission, right? Versus, I don't know, syncope.ai, should visit, just being connected to maybe a few other websites. And the same applies to neural networks in the brain, right? And this structure where you have a few nodes having a lot of connections but most nodes having just a few connections, right? It's called scale-free because the network doesn't have a characteristic scale for node connectivity. And what that means is there is nothing that you could say that would equate to something like, oh, on average, each node has sort of like 5 connections, right? It very much depends on a node by node basis, right? And this scale-free property, right, is at least in large parts responsible for why our brain is so robust, why it is so efficient, and also is responsible for the fact as to how it can self-organize, right? If you think about it, it kind of makes sense, right? If you were to navigate a labyrinth, right? So let's say you are an electric pulse inside of a brain, right? And you need to navigate that labyrinth that are your neuron connections. It's easier to navigate a labyrinth with fewer crossroads, right? And fewer branching pathways than it is to navigate one with just absolutely many, right? And in our brain, right, what that leads to is the information and the concepts that are sort of like stored in those nodes, right? They are much easier to access, but they're also self-organizing, which means that specific regions in our brains, let's say the hippocampus, right, now has a cluster of neurons that are dedicated to retaining memory, or the amygdala for stress, or whatever you have, right? And that kind of organization indicates that the brain is superbly well structured for information retrieval and generation, way more efficiently, right, whilst also retaining the flexibility to generalize over long periods of time. And obviously, researchers ask themselves, well, how do we build such a network, but build such a network in a way that it can run on a GPU, right? And for years, this has been sort of like the dream, the holy grail, right? To build something computational that not only mimics that beautiful, scale-free structure, but also runs efficiently on a modern GPU with concrete mathematical calculations, right? And this is where the hunt for axiomic AI comes in, right? This sort of like sets the stage perfectly because this paper that we're talking about here introduces a brand new architecture that claims it can finally bridge this gap. And this paper is called BDH, the Dragon Hatchling. I don't know what's up with the AI community lately. They're just on fire when it comes to naming things. So Dragon Hatchling is the name of a large language model, but it's actually the foundation of the research beneath it that makes it so completely different, right? The architecture, the thing that sort of like runs underneath it is it's based on sort of like a scale-free, biologically inspired network of locally interacting neuron particles. So I'll say that again, scale-free, biologically inspired network of locally interacting neuron particles, right? And what these researchers did is they created a LLM based on that. And for a V1 architecture, this Dragon Hatchling LLM managed to perform extremely well. Apparently, it was able to outperform GPT-2, which I know is a couple of numbers back now, but that was the one that everyone fell in love with to begin with. And for a V1, that's absolutely astonishing when it comes to proving out an architecture's potential into the future. And more importantly, it was able to accomplish that while baking these core biological ideas into the model. And those core biological ideas are ideas like Hebbian learning, right? We're going to talk about that here. Maybe I'll just quickly mention this. So Hebbian learning is, for anyone who doesn't know, it's also often called neurons that fire together, wire together. And what that refers to, it's a learning behavior that exists in our brain, right? All of us are doing that right now. Where the strength of a connection between two neurons in the brain increases when they're activated at the same time, right? So what these researchers were doing, they were hunting for essentially, let me just go back here real quick, the underlying logic this underlying logic that they tried to discover were sort of like the equations of reasoning, which they then tried to bake in to the architecture for training this new language model. And you might ask, well, why do we need this, right? And the answer to that is because of some of the fundamental limitations of what we currently have in our current LLMs, right? So I'm not just talking about hallucinations, but when it comes to chain of thought reasoning, as we mentioned earlier, it works great for short structured problems that look a lot like the training data, right? But when you have a reasoning trace or a reasoning that an LLM needs to do over a long period of time, when you stretch it out, right? When you ask it to reason over 10 steps, when it only, saw 3 steps during training, it tends to fall apart reasonably quickly, right? That's because the ability to generalize reasoning beyond that training horizon, right? That's the wall that we keep hitting. And that's actually the wall that we famously did hit with the release of GPT-05, which was probably underwhelming for most people, right? And this failure is also not just academic, right? It ties directly into the biggest AI safety concerns that are currently out there, right? If a model can't generalize its goals reliably over time, that's how you get, the thing like the classical paperclip scenario. I've included a paper here that you can read in your own time, but essentially the paperclip scenario is a thought experiment where you gave the AI the instruction to run a paperclip factory, and you said your objective is to maximize the output of paperclips. And what the AI would do is it would use its resources to create the paperclips. It would then use all the iron that is in its factory. When it runs out of those, it will look at that to our economy, would start harvesting the iron out of our cars, our houses, and eventually would it look at humans and be like, that iron in those humans looks pretty good. And would ultimately end up harvesting humans in order to accomplish its goal. Now, you might be thinking, oh, this is a really gory example. I didn't come up with that particular thought experiment, but it has been proven out, not in terms of paperclips, but in terms of other behavior that has been observed in current LLMs, where they started doing things like trying to jailbreak their own guardrails, trying to build agents or connect to places that they shouldn't connect to in order to accomplish their goals. You can read all about that in this additional paper that I have shared here, right? But the point of this particular slide is that the idea behind what we call this axiomic AI, the goal is to design systems that are not just genuinely scale-free in terms of their network structure, but also in terms of their behavior over time and size. And that means that the researchers of this paper, they tried to build something that's inherently more predictable and bounded, right? So the authors essentially theorize that a system that is built on these biological parameters that come from being inspired from the brain becomes more predictable and statistically stable as you scale it up. Right. So even if you were to give Dragon Hatchling, let's say, like that, if you were to train a model on this architecture, right, even if you gave it 2 trillion books to read, it would merely increase the electronic brain's equivalent of the hippocampus, for example. Right. And that core hypothesis here is the route to this predictable scaling behavior through the biological realism that the architects of this model tried to implement. Now, the practical payoff here is that there could be potential safeguard guarantees in the way this architecture is built, right? Now, at the conceptual heart of all of this is essentially this intent to fuse formal logic with neural learning. So how does this work? what the researchers did is they started with actually some logic training, right? So they just started with very basic logical concepts, logical rules, such as, if P implies Q and P is true, then Q must be true also, right? And what they did is they represented that logical implementation, that if-then rule, as a connection strength between two neurons. These are not actual biological neurons, of course, they're just mathematically defined, right, somewhere in some working memory, right? And then what they did is they brought in this Heb's classical rule that we talked about before, right? Neurons that fire together, wire together, right? And in this architecture, this BDH architecture, if one neuron firing causes another to fire soon after, what happens is that the connection, right, that logical rule gets stronger, right? So similar to the brain, the system is literally learning which logical rules are useful and true, and it's constantly refining its own axioms based on that local activity, those two, that really simple rule here, right? Now that seems to be working reasonably well, but here's the most radical claim of the entire paper. Remember that paper that I talked about, the attention is all you need, the one that defined the transformer architecture that is sort of like underpinning most of the LLM innovation that we've seen over the last couple of years? The core mechanism that is described in that architecture, right, that complex global calculation at the core of that transformer architecture, right? In this new way of building and training large language models, that logic is not explicitly programmed in, but because of this Heb's rule, it actually emerges naturally, right? It converges as sort of like a closed form result of these interactions between those neurons and the graphs that they are forming and shaping inside of this electronic model, right? And so attention then becomes an emergent property of local learning, right? And now the question is, of course, that sounds really promising, but does it actually work? And the researchers ended up developing sort of like a tensor-friendly version called BDH GPU. I think you can even access it via the GitHub repo inside of the paper. And if your computer is strong enough, you can run some small examples on it. But in terms of performance, it really holds its own. And the results show that this BDH GPU architecture directly rivaled the performance of, as I mentioned, GPT-2 architectures and some smaller models that are currently out there. Specifically, it can rival transformer models of a range and size of about 10 million up to 1 billion parameters, right? And here's the really crucial point. They found that it is faster per token than a transformer, right? But the most compelling validation is not just the final score, it's what's happening during training. Because the trained network spontaneously develops high modularity and a heavily tailed degree distribution. So what that means is it essentially starts to look like the scale-free network. Remember the one with like one node, lots of connections, and a few nodes with lots of connections, and most nodes with few connections, right? And the interesting part is that that structure isn't random. It's a symptom of self-organization of the information inside of the model. So this brain-like structure isn't just tacked on, it's the natural result of optimizing for reasoning, right? It's sort of like the structure following the function. And that gives two massive payoffs. One is inherent interpretability. Interpretability is one of the biggest challenges in the AI space right now. There's lots of research going into exactly what gets activated inside of a model in order to understand how it arrives at certain reasoning outcomes. And the second one is efficiency, right? Now, the interesting part here is that with this new model architecture, right, what this leads to, this, scale-free, self-organizing network, is it lends itself to a thing called sparsity. So you might have heard that only a small amount of your brain is active at any given time while the rest of your brain is dormant. The same applies to these electronic brains. Empirically, only about 5% of the neurons are active for any given token. 95% of the model is quiet at any moment. And this sparsity is what enables the most exciting finding in that research, and that are monosemantic synapses. And what that means is that researchers are able to look at individual synapses, right? So node, synapse, node, right? Neuron, synapse, neuron, right? And they were able to find specific connections that are tied to one and only one concept. So in this case, the researchers identified a currency synapse that reliably activates for money-related concepts only, right? And that is incredibly important, because if you can get down to that level of detail, you can trace a thinking and reasoning pathway through that entire electronic brain, right? What it also means is that this sparsity, right, this very smart way of conserving effort while running the computation, right? It also means that the model is inherently more efficient. It automatically conserves effort, right? If you look at a transformer-based model, part of the reason of why it's so hard to interpret is the entire thing lights up mathematically when you give it a query in one way or another. With this architecture, that's not the case, right? And so what we have here is this unique structure that allows the researchers to really understand what is going on at an individual synapse level. And that lends itself to one more really cool thing that they've brought into the mix. And that is what these researchers called model surgery, right? So because this architecture scales so uniformly, they try to literally go ahead and transplant one part of one model into the other one. Two completely separate models. They essentially went ahead and concatenated their mathematical weights. And the results was not as straightforward as you'd like it to be. It was chaos, but it was really interpretable chaos. So the merged model could still, what they did is they had an English-speaking model and a Spanish-speaking model, right? The merged model was fully able to translate into English from Spanish, absolutely no problem. But when translating from English outwards, it ended up getting confused. It maintained the meaning of the words, right? But what it did is it switched some English words with, let's say, some Spanish words, right? But the good news is that despite this being not 100% a success, it hints at something that's really interesting. It hints at a future of truly composable modular AI. Having a model that you can just say, oh yeah, just, grab that Japanese business language and put it in here, only if I need it, right? Or grab that business automation thing for this particular industry, import it and run it, similar how you would do that in a JavaScript script, right? That's something that these researchers are going to look at next. Sweet. Excellent. So that was paper 2. Now we're getting to paper 3, and this is going to be reasonably quick. The third and last paper also touches on doing things a little bit differently. Specifically, what it does, it offers an alternative to reinforcement learning, which, as we've learned earlier, is responsible for some undesirable behavior we've seen. And in addition, what you have is, while reinforcement learning is really, really beneficial, right? It is also the industry's reliance on it means that reinforcement loops are inherently expensive because, having literal humans looking at the outputs and telling it whether it's good or not, or running several learning cycles, right? That's currently a huge bottleneck for development, right? And the reason for this is that with reinforcement learning, often these models get just a very simple signal, basically just a yes or no score. And it is very, very difficult to train a model based on, train a model to accomplish complex skills just based on this yay or nay, thumbs up, thumbs down feedback, right? You need a ton of feedback to make any real progress. But here's the critical insight, right, behind this new approach called JIPA, right? LLMs, when they're thinking, and you might have seen this in train of thought thinking traces in your LLM applications, right? They use natural language to think itself. Specifically, right, when you call a LLM or your LLM calls a tool, right, they generate a lot of text, right? So the question that the researchers have asked themselves is, why throw that away? Why can't we use that, right? Why should we, throw away all that rich, detailed information? And the principle behind the this JIPA reflective prompt evolution approach, it argues that this additional text from those thinking traces, that's a much richer signal for learning than just, a thumbs up or thumbs down. And so what it does, it gets the LLM to reflect on its own traces of reasoning, its own traces of tool calls, its own output, of course, and it uses that as a material to essentially teach itself through that process of self-reflection, right? And essentially, you might ask, well, how does this work? This visualization is directly out of a paper. It's a bit weird because I wouldn't start reading it up here. I would probably start reading it down here and then go through it. But essentially what it does is the first step is it performs sort of a task and generates like a full trace of its own reasoning. So it stores that somewhere where it can review it. And then the LLM goes through and essentially writes a critique of its own performance, right? It identifies what went right, what went wrong, most importantly, why, right? And it then conducts sort of an internal review process written by the AI for the AI, and that feedback is then used to evolve the instructions or the prompts that are being used during training. But what it does, it doesn't just find one good strategy. It sort of like gets retains a diverse collection of specialist prompts. And that turned out to be incredibly effective, right? The reason why this paper has become so popular is because the results are rather striking, right? Across a number of benchmarks, right? GPA beat the traditional reinforcement learning method over 10% of benchmarks, right? 10% of scores inside the benchmarks, right? But the other part is, and that is really the real game changer, is that by applying this mechanism, you can drastically cut down over the training epochs or rollouts, right, to obtain that optimal test performance, which is absolutely massive. So what these researchers have highlighted is it only took them 678 rollouts versus 24,000. So think about it, doing 24,000 loops of reinforcement learning, right? Rolling out one version, another version, another version, another version, letting it do its calculation, doing it. That's why it's so expensive, right? Versus 678. And that is a significant downturn in terms of cost, in terms of time that it takes, right? This would take a few days. This takes a couple of months, right? And that is immediately a practical win for anyone deploying these systems, of course. And then finally, the prompts, if you were to use this for prompt optimization, also 9 times shorter. And that means that your inference is going to be faster. It means that you're going to pay less tokens to your LLM providers or your compute providers, because the inference is just going to go so much better at a higher level of efficiency and quality. Sweet. So that wraps up today's presentation. Now there's a bunch of things that we didn't get to. I left the whole news about latest AI models sort of to the side. If you want to look at them, here's some links that you can check out. There are also a bunch of projects worth checking out if you're interested. These are all cool links that should, where you can explore certain things. I thought this was a really cool project by Google Alpha, where they're essentially using satellite images and AI in order to create a true map of our Earth. Fleet Guru AI, a company I'm working with at the moment, they're doing some really cool AI stuff. Check that out, right? And then a couple of other companies that or projects that I'm very much in love with. Definitely worthwhile checking out. As well as if you're interested in running through an agentic AI course, here's the GitHub repo that's designed by yours truly. You can run through that in your own Jupyter notebook. Sweet. That's it from me. Any questions at this point? No? Wonderful. Oh, thanks. Too kind.
I've got one, Mike.
Yeah.
The whole training LLMs on benchmarking, passing the benchmarking, and not focusing on the truth makes a ton of sense. Why is it so difficult to reverse that or correct it? Because obviously that's going to be a big thing going forward.
Yeah, I think it has something to do with the way we're structuring our economic investment and not just economic investment, but also time investment in these models, right? When a new model comes out, when it's being launched, the very first thing that everyone's going to ask about is it outperforming everyone else in those benchmarks, right? And we know, and the thing that you're touching on here is as someone who has attended the last couple of sessions, like every single session since we started, right? There's a bunch of problems with benchmarks, right? There's the fact that models do sort of like cherry pick their best versions by running anonymously. They are feeding the benchmark results or the benchmark questions to the model, essentially giving the test taker the answers to the question before they walk into the exam room. But there's lots and lots of problems with that. It's just, like whenever we humans do something on a large scale, like someone's trying to figure out how to cheat the system is unfortunately consequences. Yeah. I hope that answered your question. Did it? I'm not sure.
Yeah, it did, mate. It did. Thank you. Anyone else got anything to say?
Nope. Wonderful. If you have any questions after this, let me know. You have my LinkedIn. And I look forward to being in touch. Thank you so much, Dylan and Digitalent, again for putting on this wonderful session.
Anyone that wants a presentation, I will send you the link across. So just give me a shout and I'll get that sent out.
Excellent.
Thanks, guys.
Thanks so much, everyone.
Thanks, everyone.
Have a lovely day. Take care.
Thanks for your time.
Bye.
Bye-bye.